What we have to do today is we have inhibition and summation at the axon hillock, or of the trigger zone, in a neuron. So we're going to walk our way through that, and finally at the end we want to get to the point where we talk about the reflex arc. So what we're going to do today is we're going to bring up where we ended yesterday. We're going to talk about EPSP, summation, and membrane resistance. What we did last time is we laid out the idea of how neurotransmitter was being released. We laid out how the idea of neurotransmitter being released at a presynaptic element would then bind to receptors on the postsynaptic side. Last time we emphasized the opening of ligand-gated ionotropic channels, those that were responsive in the central nervous system primarily to glutamate. The opening of those channels allowed for the influx of sodium into the input region of neurons. That sodium would generate a depolarization. But the depolarization generated by the neurotransmitter released at an individual synapse, that depolarization tends to be small, no more than a fraction of a millivolt. And so then by the time that potential propagates over the input region of the membrane, because that input region contains potassium leak channels, much of that charge leaks out. So the size of the potential generated at the synaptic site, which may be a millivolt at most, may only be a fraction of a millivolt by the time it reaches the trigger zone. Now remember that the trigger zone, the function of the trigger zone, is the site where we have clustered together those voltage-gated channels, and its purpose now is to sense the amount of positive charge on the cytoplasmic side of the membrane. If there's adequate amounts of positive charge on the cytoplasmic side of the membrane at the trigger zone, then the voltage-gated sodium channels will begin to fire and propagate action potentials along the conductor region. So the whole purpose of that is now to bring to bear the depolarization of many, many synapses onto the trigger zone. That means we have to summate or add together EPSPs from multiple synaptic sites to bring to bear enough positive charge at the trigger zone to organize enough voltage-gated sodium channels to open to trigger an action potential and propagate that potential. But one of the problems we're going to run into is that the amplitude of the EPSPs decays because of the leak channels. This brings us then to the idea of Ohm's law. Ohm's law simply says that the voltage is equal to the membrane resistance times the current. Now we've simplified this a lot. We've simplified it to only deal with the membrane, and we've also simplified it to talk about the membrane resistance in terms of the potassium channels. So the membrane resistance really is, you can think of it, as we closed last time, as a leaky garden hose. The more holes you have in the hose, the leakier it is. And in this case, the more potassium channels we have in the membrane, the leakier it is. So if we analogize the input to these input regions, the synaptic inputs, to a faucet and a garden hose, when you turn on the faucet, if you have a leaky garden hose, not much water comes out the other end. Well, similarly here, if you have a leaky membrane, when you put a voltage on that membrane, you have a current flow, then that voltage will decay through the leak channels by the time we reach the trigger zone. In other words, these potentials are going to get smaller with distance. And so we're going to see then, because of the fact that they get smaller with distance, it will take many more of these synaptic inputs to reach threshold. And we always walk through this initially by talking about the depolarization, EPSP, and the role of the EPSP in adding charge. But a major, major function of the nervous system, and if you take another course in neurobiology, you'll really see an emphasis on this idea of inhibition. For the most part, the way our nervous systems function is to use inhibition to keep things under control. Without adequate inhibition, the whole system runs out of control. And so what we find then is inhibition becomes a really, really important aspect of regulating nervous system function. So I want to spend a little bit of time here talking about the role of inhibition in the input region. We're going to lay out another one of the pineapple neurons. And interspersed among the excitatory synapses here, which give rise to EPSPs, we're now going to give attention to the neurotransmitters GABA and glycine. The neurotransmitters GABA and glycine will now open ligand-gated ionotropic channels, just as glutamate opened a ligand-gated ionotropic channel. But what's different here is that the neurotransmitters GABA and glycine now will open a chloride channel. Now the chloride channel, I should put this down here, will generate an inhibitory postsynaptic potential. The opening of the chloride channel, though, although it will produce an inhibitory postsynaptic potential, a better way of thinking about what the chloride is going to do is to concentrate on the equilibrium potential for chloride. Remember, all of these ions have their own equilibrium potential. And remember the mantra. The membrane potential seeks the equilibrium potential of the ion whose permeability is dominant. So if we open up a whole bunch of these chloride channels, that means the predominant permeability is now going to be chloride. So the membrane potential is going to seek the equilibrium potential for chloride. Now, the equilibrium potential for chloride, for the most part, in many cases, will be more negative than the resting membrane potential. So what that will do is it will drive the resting membrane potential toward the equilibrium potential for chloride. It will make the resting membrane potential more negative. This is going to be a so-called hyperpolarization. But what happens if the equilibrium potential for chloride is right at the resting membrane potential? Then you open the chloride channels and the membrane potential doesn't change. It's fixed at the equilibrium potential for chloride. But it's still inhibitory, because if we try to drive the membrane potential away from the equilibrium potential for chloride with EPSPs, if the dominant permeability is to chloride, we're stuck there. That's even true if the equilibrium potential for chloride is more positive than the resting membrane potential, in which case the opening of the chloride channels will depolarize the membrane because it will go to the equilibrium potential for chloride, but now once it reaches the equilibrium potential for chloride, it's fixed there. It won't change. So even if we put in more depolarization, it's fixed at that point. So although you'll often hear inhibition referred to as a hyperpolarization, it needn't be a hyperpolarization. The more important aspect of the chloride effect is the effect of driving the membrane potential and holding it at the equilibrium potential for chloride. But there's another aspect of this I'll emphasize at this point, and that is that when we open these chloride channels, we drive the membrane potential to equilibrium potential for chloride. Having the chloride channels open is pretty much the same thing as adding potassium leak channels. And what I mean by that is we can change the membrane resistance, R sub m. So that for a given voltage, if the current is fixed, and let's say we open a fixed number of channels, that's the current. A number of ions will move through channels that we open. That's a fixed number. If this number is fixed and we change this number to make it either higher or lower, what effect does that have on the voltage? It's a linear equation. So if R sub m goes up, this number doesn't change, the voltage goes up. If R sub m goes down and this number doesn't change, the voltage goes down. So now we can begin to see how making the membrane either leakier or less leaky through inhibition, we can regulate the amplitude of the EPSPs. And then from there, we'll also see there's another equation, tau is equal to R sub m C sub m. R sub m is the major player here because C sub m is fixed. It's always the same. So if we change R sub m, if R sub m goes down, tau gets shorter. If R sub m goes up, tau gets longer. So now we'll see that inhibition has two effects. It both affects the amplitude of the EPSPs and also affects the duration of the EPSPs. So if we reduce R sub m, these potentials get smaller and shorter. That means it's going to take many, many more of these to add together to reach threshold, and we'll talk about that. And then from there, we'll talk about the reflex arc. But let's start here with our typical neuron. The major players in this are the input region and the conductal region. And the ideas that we introduced over the last couple of discussions, where we had here at this region called the trigger zone. That were at the trigger zone, we had voltage voltage-gated channels clustered. And then we emphasize that all over this input region, there may be hundreds, or more likely thousands, of these output regions of other neurons. And in blue, we described these as excitatory synapses. As excitatory synapses, they were, for the most part, in the nervous system, releasing the amino acid glutamate. We then emphasized that the glutamate would bind to glutamate receptors, where these are the glutamate receptors. These are the ligand-gated ionotropic channels. So remember, when the glutamate's released from these axon terminals through vesicular exocytosis and the glutamate binds to these receptors, it generates a depolarization. This depolarization results from sodium influx. But one of the major ideas that we emphasized last time is that the number of receptors at this site may be no more than a few hundred. So we're limited by the number of receptors that can bind a neurotransmitter, open and let ions come in. And if we took a recording here, what we would see is that the response to the release of the neurotransmitter in a single vesicle would look a little like this. It would go from minus 70 millivolts, depolarize, we'll come back down again, and the depolarization at this site would be less than 1 millivolt. So it would go from minus 70 millivolts to more or less minus 69 millivolts. But remember, that's what's happening right here at the dendrite on this input region way out at the dendrite. And that between the dendrite here and the trigger zone is a vast stretch of membrane. The vast stretch of membrane of other dendrites, the vast stretch of membrane of the cell body. And that vast stretch of membrane lacks voltage-gated channels. Remember, one of the major concepts we drove home was the input region lacks voltage-gated channels. But what it doesn't lack, what it is characterized by, and this is true for all membranes, are these potassium leak channels. Now, this brings us back to that early discussion we had in our imaginary or our thought experiment, where we clustered voltage-gated channels at one end, fired an action potential, and asked the question, what happened to that depolarization as it tried to propagate along the membrane that contained only leak channels? We have the same story here. In other words, the potential, the depolarization of 1 millivolt that's put on the membrane here, this positive charge in the form of potassium is going to leak out through the leak channels. So what does that tell you about the amplitude of this potential as it moves across the membrane toward the trigger zone? If the positive charge is leaking out, what's going to happen to the amplitude? It's going to get smaller. It's going to decay. Because remember, what we're really measuring here with this depolarization is the number of positive charges. And the number of positive charges is going to become fewer and fewer as they leak across the membrane, as they approach the trigger zone. Now, let's think about this in a couple of ways. Let's think about the case where we have many potassium leak channels in the input region. If we have many potassium leak channels, this is like a leaky garden hose. This is like leaky membrane. So if it's leaky membrane, that means this amplitude is going to decay considerably by the time it reaches the trigger zone. The converse of that is to say that we have few potassium leak channels in the input region. In which case we have a tight membrane. We can now describe the tight and leaky membrane in terms of their resistance to ion flow. If it's a tight membrane and not many ions can leak out across it, we can say that this tight membrane has a high membrane resistance. We can say R sub m is high. On the other hand, where we have a leaky membrane, we can say R sub m is low. So if you hold on to the idea now that R sub m is more or less proportional to the leakiness of the membrane. I think this should be a Y. So the more leaky the membrane, the leakier the membrane, the lower the membrane resistance. The less leaky the membrane, the higher the membrane resistance. Well, why is that important? Well, it becomes important because we can think about the voltage. In other words, this depolarization that we saw here, this voltage, this change in voltage, is equal to R sub m times I. Now, I is simply current. I should label this too as Ohm's law. And Ohm's law simply says that the depolarization of the membrane, the change in voltage, delta V, is equal to the resistance of the membrane times the ion flow. Ion flow is just another term to mean current. The current is measured in coulombs per second. It's just the number of charges moving. And if we recognize here what we're doing is we're opening these ligand-gated channels. And when we open the ligand-gated channels, sodium flows in. What we're talking about is a flow of sodium. That's an ion current. That's the movement of ions. Now, if the movement of ions is determined by the number of these receptors, that is, if we have fewer receptors than we have neurotransmitter, then we open up all these receptors and the ions move in. So that gives you a current, it gives you a number of ions moving per unit time. So that's this current, I. More or less, they're always pretty much the same number here, a few hundred of them. So that means the amount of current that will flow at this one synapse is pretty much fixed. We can't change that much. So that means then we can say the voltage change, the delta V, the depolarization is equal to R sub m times the number of ions moving. Well, if we think about this now with an R sub m as being a big number or a small number, if R sub m is high, if we have a tight membrane, if we have very few pathways for the potassium to leak out. Conceptually, we said if we have few pathways for the potassium to leak out, most of this charge will reach the trigger zone and depolarize the membrane. we can now provide a quantitative estimate of that by saying that it's dependent upon Rm. That this number, the number of ions that move at a synapse, is pretty much always the same. But then R sub m now will determine the amplitude of the depolarization. The higher R sub m, the tighter the membrane, the bigger the depolarization. The lower R sub m, the leakier the membrane, the smaller the depolarization. So the upshot of that is that when this 1 millivolt potential is produced out here and it propagates along the membrane, when it arrives at this site, the depolarization you see may go from minus 70 millivolts to maybe 69.9 millivolts. It may be small indeed. Now, if the membrane resistance is higher, maybe this, rather than going from 70 to 69.9, maybe it goes from 70 to 69.5. But all we're saying here is, depending upon how leaky the membrane is, that will tell us the depolarization that's recognized at the trigger zone. The other really important idea to recognize here is that the resting membrane potential is about minus 70 millivolts. But remember, to get these voltage-gated channels to open, we have to reach threshold. And it's not a hard and fast number, but more or less, that's about minus 55 millivolts. So if that's minus 55 millivolts, then we have to go from 70 to minus 55. We need to go 15 millivolts. If each of these potentials has only depolarized the membrane here by 1/10 of a millivolt, we need 150 of these to go the 15 millivolts. So that's a long-winded way of saying that one of these synapses, opening all of the receptors at one of these synapses, produces a practically infinitesimally small change in the membrane potential here. It tells us that for this membrane at the site of the trigger zone to receive adequate positive charge to open these voltage-gated sodium channels, to reach that threshold is going to require the nearly simultaneous activation of maybe 150 of these individual excitatory synapses, each one adding its depolarization, such that the depolarizations from multiple synaptic sites are required to drive the membrane potential. At the trigger zone. To threshold. This idea of requiring multiple synaptic inputs is said to be the summation. Said to be the summation of excitatory post-synaptic potentials. So we're adding together each one of these tiny depolarizations produced by the release of probably one vesicle's worth of neurotransmitter. Each of these tiny potentials needs to add together to provide just a little bit of oomph to provide sufficient positive charge at the trigger zone to get these voltage-gated channels to open, such that once we depolarize by summating EPSPs, the summation of these EPSPs will drive the membrane potential to threshold, and at that point fire an action potential. Once you have enough sodium coming in through these voltage-gated sodium channels, you're opening all of those voltage-gated channels in the neighborhood. That's the beginning of the all or none, stereotyped, unchanging, invariant action potential, which will go up to plus 40 millivolts, and then with the potassium channels opening, repolarize. So, Any questions about this idea of summation? Yes?
Is there a disease that actually has too many potassium channels in the lead?
Is there a disease that has too many potassium leak channels? Not that I know of, but certainly there will be pathologies that are going to affect the next step, which is going to be inhibition. So our next step here is going to be interspersed among these excitatory synapses, inhibitory synapses. And the role of the inhibitory synapse is, in fact, to change the membrane permeability to chloride. And as far as this membrane is concerned, it does not matter whether potassium is going out or chloride's coming in. That's all about the idea that we're going to change the membrane resistance here. And so what you're saying is, can we have an effect on the membrane resistance by changing the number of leak channels? Are there pathologies like that? Not that I know of. Are there pathologies where there are problems with the number of inhibitory synapses that are effective? Absolutely. And that then will affect the membrane resistance and be the same thing as what you're envisioning with the changing and differences in potassium leak channels. Anything else? Okay, so what I'm going to do along this membrane is I'm going to put some red circles, and then I'm going to take these red circles and label the red circles as inhibitory synapses. But I want to take a moment on the upper panel to describe inhibitory synaptic transmission. For the most part, much of what we've learned up to now is applicable here. This is going to be the axon terminal of an inhibitory neuron. And for the most part, if you look at the axon terminal of this inhibitory neuron, it looks like excitatory synapses. It's chock full of synaptic vesicles. Some of the synaptic vesicles are clustered up against the membrane. They're docked. And beside those vesicles will be these voltage-gated calcium channels. So then, of course, when an action potential arrives at the axon terminal, and remember, the long-distance communication in inhibitory neurons is the same as excitatory neurons, such that if up here there are the voltage-gated sodium channels, the voltage-gated sodium channels will deliver positive charge. That positive charge tells these voltage-gated calcium channels to open, and the opening of the calcium channels allows calcium to come in. From there, the story is pretty much the same. Calcium binds to synaptotagmin and then allows for the winding together of the T snares and V snares. And when they wind together, just as we saw before, that vesicle will fuse with the plasma membrane and release its contents. So this is going to be calcium triggering. This is calcium triggering of neurotransmitter. Let me just do it this way. Triggering of exocytosis. Now this is where we begin to see some variation. At this point, the triggering of exocytosis now releases a new kind of neurotransmitter, either gamma amino butyric acid, which we abbreviate as GABA, or the amino acid glycine. In the brain, most of the inhibitory neurotransmitters are GABA, so let's talk about GABA. So now we have released this neurotransmitter called Gaba. And we see the same pattern as before. Over here on the postsynaptic membrane, this is going to be the postsynaptic cell. There will be in this membrane another set of channels that we've seen before. And these we're going to label as ligand-gated. Ionotropic channels. Now, in this particular case, these ligand-gated ionotropic channels will have on their extracellular region facing the axon terminal. They will have sites that are Gaba receptor sites. So that the neurotransmitter here, which we talked about being released by exocytosis, that neurotransmitter binds to these receptors. So at this point, everything is the same as what we talked about for excitatory synapses. But now there's a change. And what we find here is that GABA and glycine open channels to increase chloride permeability. That's just another way of saying that these are chloride channels. And that they will now, in some cases at least, allow chloride to go from the outside to the inside. What's the charge on chloride? It's negative. So if chloride is coming in, and we start out with a membrane potential of minus 70 millivolts, if chloride comes in at that site, what's that going to do to the membrane potential? It's going to hyperpolarize it. It's going to make it more negative. So now we can envision, and this is true, it's not a complete truth, but it's true that we can now envision a case where we have the membrane potential at minus 70 millivolts. And this is time. And so now we can see, we start out, it's stable. This is the resting membrane potential. And at this point now, we open chloride channels. And if this dotted line here represents the equilibrium potential for chloride, if the equilibrium potential for chloride, pick a number here, is say minus 75 millivolts, then the membrane potential seeks the equilibrium potential for the ion whose permeability is dominant. This membrane potential is going to be headed toward minus 75 millivolts. If we superimpose precisely in time, and let me give this a name, this is called an inhibitory postsynaptic potential. If we precisely superimpose on top of this a depolarization, and this is a depolarization from opening glutamate channels, then if we superimpose these, if this is a plus 5 millivolts and this is a minus 5 millivolts, I think you can see how they cancel each other out. Basically, there's no change. So we had them perfectly superimposed in time and superimposed in terms of their depolarization and hyperpolarization, there's no change. So that would mean that we are canceling out, if we go back to the upper panel, in that simple view, we can now use these inhibitory synapses to open chloride channels in our first description here, the opening of these chloride channels can now offset depolarizations produced by the excitatory synapses. Now, you okay with that? Straightforward, yes.
So, do the postsynaptic neurons of inhibitory neurons, do they always have just chloride channels instead of steroids?
So the question here is, if we look at the postsynaptic membrane right on the other side of one of these inhibitory synapses, the only receptors we'll have here will be Gaba receptors. And even if we would have glutamate receptors, it wouldn't much matter because they wouldn't bind to Gaba. Okay? And but what you're looking at here and what you're envisioning is you're asking the question, are the effects of the neurotransmitters restricted to the narrow regions of the membrane immediately beneath the postsynaptic element? And they are. You don't see much of this neurotransmitter, partly because of the glial cells wandering from place to place and affecting receptors outside of that particular synapse. So the GABA released here will affect GABA receptors here. The glutamate released here will affect glutamate receptors here, right beneath that membrane. Okay? Anything else? Yes?
So do the astrocytes pick up all the extra neurotransmitters like for the previous example with glutamate, if they're going to do glutamine, we still do the same thing with GABA and turn it back into something else just to pick up the extra?
Will the glial cells absorb and take up the neurotransmitter GABA like we talked about taking up glutamate? Yes, they take it up the same way. It's pretty much the same thing. I'm not sure if they convert it back to something inactive. I'm not sure of that.
So is it still the same astrocyte that's doing all the same?
It could be the same astrocyte. It's just a question of whether or not it has the appropriate sodium-different co-transporters on them to move into cytoplasm. Yes?
Sorry, is the red circle, is it another neuron?
So is the red circle another neuron? Yes. This is an output region of another neuron. So you would trace this back to an axon to a cell body. And maybe these two would have the same cell body, but on a given input region of neuron, you may have several hundred different inhibitory neurons impinging on that membrane. It's hard to imagine the number of synapses out here. There'll be hundreds or thousands of excitatory synapses and maybe tens or hundreds of inhibitory synapses, generated from maybe tens or hundreds of different neurons. Okay. Let's now think about the other possibilities. If we go to the upper panel again and we at this point we describe, rather than setting the E sub Cl more negative, let's take the other possibility. And we set the E sub Cl equal to the resting membrane potential. Remember that by opening these chloride channels, the membrane potential seeks the equilibrium potential for the ion whose permeability is dominant. Now, the equilibrium potential is the same as the resting membrane potential. So how is that inhibitory? Well, it's inhibitory, again, because the E sub Cl will be fixed at this point. If we have mostly open chloride channels, if we now try to add a little bit of depolarization on that, it's going to not be very effective because the resting membrane potential is going to be fixed, clamped at the equilibrium potential for chloride. The same thing is true is if you even set the equilibrium potential for chloride at, say, minus 60 millivolts. Then when the chloride channels are opened, chloride actually flows out, driving the membrane potential to the equilibrium potential for chloride. And it's depolarizing. And of course, immediately you say, well, every time we see something depolarizing, it's driving the membrane potential toward threshold. But remember, if this is a minus 60 millivolts, but if threshold is, say, minus 50 millivolts, you're still well short of threshold. And so then you'll fix the membrane potential at the equilibrium potential for chloride. And even if it's more positive, it continues to be inhibitory because you're not driving the membrane potential above threshold. So regardless of where you set the equilibrium potential for chloride, because of the story of driving the membrane potential to the equilibrium potential for the ion whose permeability is dominant, you'll inhibit the membrane potential by keeping the membrane potential fixed at that point. It's an important concept. But there's another idea I want to present here, and this comes back to one of the questions about pathology, and that is that we described the membrane resistance as being proportional to the leakiness of the membrane. And we emphasized initially that our only leakiness was from the open potassium leak channels. We didn't have any other character to invoke. But now we have another set of channels. We now have a set of channels, but they're chloride channels. And it really doesn't matter to the cell whether you're using potassium channels to leave or chloride channels to bring chloride in, whether potassium leaves or chloride comes in. As long as you're fixing the membrane potential, it doesn't much matter. But what we're doing here is by adding chloride channels, I'm running out of room, we can say up here that increasing the number of open chloride channels, increasing the number of open chloride channels reduces the membrane resistance, R sub m. So initially we talked about affecting R sub m simply through the use of the leak channels. But now we have an additional way to do that. We can now affect R sub m by opening the chloride channels. So now we're back to Ohm's law. If the voltage, the depolarization produced by one of these excitatory synapses is dependent upon the membrane resistance, and initially we invoked the membrane resistance being entirely dependent upon the potassium leak channels, but now let's do it with chloride channels. Remember that all we're doing here is using the chloride channels to change the membrane resistance. So we open a whole bunch of chloride channels. What's that going to do to R sub m? It's going to make it go down. If this number gets smaller and this current number doesn't change because they only have a certain number of receptors and number of open channels, what's that going to do to the amplitude of the EPSP? Going to make it smaller. So that means if we make this membrane leakier, that means all of these EPSPs, as they travel across that leaky membrane, will get smaller. So that means if we needed 150 of these EPSPs to add together at the trigger zone, because now we've increased the permeability to chloride, we've made the membrane resistance smaller. That means now we don't need 150. Now maybe we need 200 or 250. So now by changing the membrane resistance using the number of open chloride channels, we can now regulate the number of excitatory synapses that must be activated to bring the membrane to threshold here and fire an action potential. So we can regulate the number of synapses necessary to bring this membrane to threshold by regulating the number of inhibitory synapses that are opening chloride channels. That's the importance of chloride. Well, if you take other courses, you'll drill down into the importance of this inhibition. But let me just say a couple of words on it. First is that many seizure disorders appear to be as a result of lacking inhibition. Something happens in the nervous system and the number of inhibitory synapses is broken. We don't have enough inhibition. So that under normal, everyday circumstances, the nervous system is functioning just fine. But something happens, and there isn't enough inhibition to overcome the excitatory input to a set of these neurons. And they start to fire out of control. And then their neighbors start to fire out of control. And their neighbors begin to fire out of control, and you get a seizure disorder. And that seizure disorder is frequently, it appears, a result of a lack of the number of chloride channels, a lack of inhibition. Again, back to your question of can we change the potassium? Well, leak channels, probably not. But a lack of chloride input is a really big problem. So any questions to there? Yes?
So that's a lack of GABA?
So it could be a lack of GABA. So and let's phrase it slightly differently though. And it could be a lack of the number of GABA neurons or a lack of the number of GABA synapses. So the result is too little GABA is being released. And in fact, in many cases, it depends on different seizure disorders, but some seizure disorders are pretty well regulated by what we call chloride channel agonists. They'll often use Valium and Valium diazepam derivatives. Diazepam derivatives they don't open the channels themselves, but they're an allosteric effect. But regardless of that, what they're doing is they are affecting the probability of opening chloride channels. And so you can control some seizure disorders by giving Valium or other diazepams, which increase the activity of the chloride channels. Okay, last couple of minutes. What I'm going to do here, the back panel, I'm going to draw a picture that we have seen before and we'll see again. Well, this is just going to be a slight modification. So where we had a stretch receptor before, stretch-activated channel, and a finger, we're now going to put a stretch-activated input region. This is a stretch receptor neuron. It's a stretch receptor of a neuron in a muscle of the leg called the quadriceps. And what we're going to do is we're going to follow this neuron from the muscle to the dorsal root ganglion, just like we did last time, and then into the central nervous system, where this neuron now is going to send a process into the central nervous system, and it will synapse directly onto a lower motor neuron, and this lower motor neuron now will send a process out and back to the muscle. And what I want to leave you with is when you go to the doctor and you sit on the gurney there, and they come up with one of those funky triangular hammers and they whack you in the knee, what they're doing is they're pulling on the stretch receptor. And what you should try to figure out between now and tomorrow is why your leg kicks up, and we'll talk about that. That's the tendon tap reflex.